Good morning. This video is going to go over the transmission of a nerve impulse, otherwise known as the action potential. So what's happening chemically and electrically to allow the impulse to travel from the cell body down to the axon terminals and then across the synapse to the next neuron or the dendrites of the next neuron. So before we get started with how this works, we need to understand what's happening to the neuron in a point of rest. So when the neuron is not actively conducting an electrical impulse, it has what's called a resting potential. And this refers to what's happening electrically and chemically to the neuron. The plasma membrane at rest is polarized, and that means that there's a difference in charge between the inside, this is the inside of the cell or the inside of the neuron, and the outside of the neuron. So inside of the neuron is typically going to be potassium. It's going to gather together, potassium ions will gather together on the inside, and on the outside it's going to be sodium. The resting potential electrically is about -70 millivolts. Now, you will notice that there is sodium and potassium both have a positive charge. However, the potassium is more negative than the sodium. So what happens is that because these are less positive or they're more negative, in a typical resting potential, the inside of the neuron is going to be more negative compared to the outside, which is going to be more positive. And that's where you get the -70 millivolts here. The maintenance of a resting potential is a really active process. It says resting, but in order to, keep this -70 millivolts of charge difference between the inside and the outside, there has to be something called the sodium-potassium pump. And that's going to be actively exchanging sodium and potassium ions to make sure that we have this uneven distribution of charge on either side of the membrane. So typically it will expel 3 sodium ions for every 2 potassium ions that are let in. So these things can go across, potassium and sodium can diffuse across. However, the sodium potassium pump is going to keep the sodiums, as many sodiums as they can inside, and as many potassiums inside, and as many sodiums outside as it can in order to maintain this resting potential. And it's going to rely on ATP to do that. So the neuron is at rest, it's polarized. Inside is more negative than the outside. And a stimulus comes. So what's a stimulus? Well, these are going to be things that are going to excite the neuron. So it could include light, it can include sound, pressure, chemicals, neurotransmitters. These are stimulus. So anything that's going to cause the process of nerve impulse to occur. Once the neuron is excited through one of these types of stimulus, so light, sound, pressure, chemical, or neurotransmitters, what's going to happen is the next stage, which is called depolarization. So what's going to happen is that the permeability of that cell membrane of the neuron membrane is going to change. And it's going to actually allow those sodiums that were all on the outside of the neuron to start flowing in. And this is going to cause now a change in how the membrane polarity is. So remember that it was more negative on the inside than it was on the outside. So now that we're letting all of these sodiums in, which were more positive, right, than the potassium, we're going to end up having a membrane that is going to become more positive on the inside than it is on the outside. So there's a swap in the polarity. And this swap then is going to continue, and you can kind of see in this diagram here, here is this section where depolarization is occurring. So here's another diagram that's kind of showing this process. So we've got all of these sodiums that are coming in. There are some potassiums that are going out as well, but the influx of sodium is so large that instead of now having a -70 millivolt difference in charge, we are now going to have a +40, which means that the inside is going to become more positive than the outside was. So depolarization is going to be sodium coming in and the charge difference between the outside and the inside changing. So instead of this being more negative, the inside is now going to be positive. So right, we went from a negative inside to a positive inside. So this, if the stimulus is strong enough and the influx of sodium ion is great enough, the depolarization actually is going to activate a nerve impulse, which we call in biology an action potential. Okay, so here was the resting potential. A stimulus is going to cause this depolarization to occur, right? And as soon as we get to about plus 40, so the inside is plus 40 millivolts, that's going to trigger an action potential. Now, an action potential then is this nerve impulse. It is an all or nothing response. So the impulse is either going to be conducted over the entire length of the axon, or it's not going to happen at all. Like, we can't have like a partial impulse. So once the stimulation happens, then it's going to be impulse or no impulse. And again, we have to make sure that we're getting to that plus 40 in order for that impulse to occur. After the action potential then is generated, what's going to happen is repolarization. So this happens almost immediately after the action potential, and the neuron membrane then is basically going to shut off these gates to the sodium ions. So it is going to stop letting these positive ions into the inside of the cell. And at the same time, the potassium ions are going to start to diffuse out in order to try and restore the negative charge on the inside of the membrane. So what we want to do is we want to get that membrane back down to what its resting potential was, where the inside is more negative than the outside at the negative 70. So this process is called repolarization. Now the sodium-potassium pump is going to again be put into action during repolarization, because remember, this is the pump that's trying to maintain that resting potential when a neuron is on rest. It's really going to be working extra hard in order to go back to that resting potential after depolarization and the action potential is generated. So it will pump excess sodiums out of the cell, and then it'll bring potassium ions back into the cell. So here's a great diagram that kind of shows these three stages. So again, here's your cell membrane here in yellow, right? The inside of the cell is down here, outside of the cell is outside. The outside of the cell during resting potential has more sodiums than the inside of the cell. The inside of the cell has more potassiums than the out. There's movement of sodium and potassium across the membrane. So remember, there are 3 sodiums that get pumped out for every 2 that get let in. So it's kind of electrically even in order to maintain this negative 70 millivolt charge on the inside. So the inside is more negative than the outside. And so then once you get down here and a stimulus comes, the depolarization occurs, those sodium gates are opened up in the cell membrane, and sodium starts rushing in very, very quickly. Some potassium is going to continue to go out, but really it's the sodium that's rushing in that's going to cause this charge then to start to go up, so that we end up with positive 40, between 30 and 40 is what the charge is going to be, millivolts, inside the cell. So we went from negative to positive. The action potential is going to be generated, which is the actual nerve impulse. And then repolarization is going to occur, where the sodium and the potassium pump are going to start working in a high gear to pump the sodium back out of the cell and bring potassium back into the cell in order to get back down to that negative 70 millivolts. So that is how electrical impulses are traveled along the course of a neuron. And this happens in sections. So you start, the first part of the neuron might be in resting potential, then it might go into depolarization and repolarization, and then behind it, it's still a resting potential. So it doesn't just happen like all at once. These things are going to occur kind of all along the length of the entire neuron. So just to kind of recap one more time, the neuron at rest is polarized. Inside is more negative than the outside. Stimulus changes the membrane permeability, allowing the sodiums to come in. Depolarization occurs, and if we get it high enough, so plus 40, then an action potential occurs. Action potential will travel along the entire length of the neuron. Then the neuron will repolarize using the sodium-potassium pump to pump those sodiums back out, bring the potassium back in order to go back to resting potential. So last thing is what happens at the very end. Then the action potential reaches the axon terminals. It's going to cause these chemicals that are located in the synapse to get dumped. Located in the axon terminal. They will dump all of these neurotransmitters into the synapse, or the gap between the two, and those synapses then will bind to the membrane of the next neuron. Those chemicals are called neurotransmitters. So these are what we call that are released at the end of the axon terminals. Some examples of neurotransmitters are serotonin, norepinephrine, acetylcholine is a big one. We're going to see acetylcholine being dumped in those synapses that cause a lot of different actions to occur. Serotonin primarily affects mood, social behavior, appetite, and digestion. Norepinephrine is both a hormone and a neurotransmitter, and it's responsible for your fight or flight response. And acetylcholine does all kinds of things in the body, especially having to do with your muscular system. So that's why we say that nerve impulses are electrochemical, because the action potential along the axon is actually electrical, but it's being triggered by a chemical reaction that's occurring with the sodium and the potassiums traveling across the membrane.